Good morning, everyone, and thank you for joining us. Today, we'll be presenting thermal management and advanced semiconductor packaging technologies. This work was completed under the guidance of Dr. Sharifi and Dr. Asadi, combining course concepts, recent literature, and real industrial practice. In modern electronics, from smartphones to data centers and AI accelerators, one of the main performance limits is no longer just transistor count, but heat. As devices become smaller, faster, and more power dense, we have to ask, how do we remove all that heat without sacrificing performance or reliability? Our focus is on how engineers handle this challenge inside advanced semiconductor packages, especially 3D integrated circuits and System in Package (SiP). We'll look at where the heat comes from, how it moves inside complex packages, and the tools and design strategies used to control it. By the end, you'll see why thermal management is now a core part of semiconductor design and not just an add-on cooling accessory. Here's an overview of what we'll cover. We'll start with a brief introduction to advanced semiconductor packaging and explain why packaging itself has become a performance enabler. Then we'll discuss why advanced packaging increases thermal challenges, focusing on power density and tight integration. Next, we'll cover the technical foundations, an overview of 3D ICs and system in package, heat generation in stacked dies, the role of interconnects, thermal interfaces, thermal via heat spreaders, and TIMs. We'll then look at system-level methods, hotspot mitigation, dynamic power and thermal management, and how simulation and testing are used to validate designs. To ground everything in real applications, we'll present two case studies, one in AI processors and one in RF communication modules, and close with future trends and a brief summary. As electronic devices advance, they pack more transistors, run at higher speeds, and shrink in size. All of that concentrates power into a tiny volume, and almost all electrical power eventually becomes heat. Without careful thermal design, temperatures rise quickly. Excess heat slows down transistors, shifts timing, and accelerates reliability problems like electromigration, delamination, and mechanical stress. In extreme cases, hotspots can cause permanent damage or failure. For advanced packaging, thermal management is a primary design constraint. It affects die placement, material selection, and even system level architecture. In this presentation, we'll connect the basic physics of heat flow with practical engineering solutions and show how designers balance performance, cost, and reliability in products like smartphones, servers, and AI accelerators. Advanced packaging improves performance, but it also makes thermal behavior more complicated. In older 2D layouts, each chip had a relatively direct path to a heat spreader or heat sink. In contrast, 3D ICs and SiPs often place components very close together, sometimes vertically stacked and sometimes densely clustered side by side. This tight integration creates thermal coupling. When one die heats up, nearby dies warm up too, even if they're lightly loaded. Heterogeneous integration, mixing logic, memory, RF, analog, and power devices means different parts of the package have very different power profiles. The result is a highly non-uniform dynamic temperature map. Traditional cooling, like a single heat sink or fan, mainly interacts with the outer surface of the package. While many critical components are buried inside, designers are forced to think in three dimensions, planning internal heat paths through materials, vias, and interfaces. Without this planning, high thermal density leads to timing errors, throttling, shorter lifetime, and potential field failures. To see where heat is generated, we first need to picture 3D ICs and SiPs. A 3D integrated circuit vertically stacks multiple dies, often connected with through silicon vias, TSVs. This reduces signal distance between logic and memory, improving bandwidth and energy efficiency. However, some dies end up buried in the middle, farther from cooling surfaces. A system in package integrates multiple chips, processors, memory, sensors, RF front ends, power management, and more into a single compact module. They may be arranged side by side in partial stacks or over a interposer in a 2.5D/3D hybrid. SIPs are especially important where board space is limited, such as smartphones and wearables. Both architectures offer higher performance and smaller footprints, but they also increase power density and create more complex thermal paths. Choices like which die goes on top, which is buried, and how they're interconnected are now influenced as much by thermal concerns as by electrical or mechanical ones. In stacked dies, heat does not simply flow up and out. It must move through multiple layers of silicon, bonding materials, interconnects, and molding compounds before it reaches a heat spreader or sink. Each layer has different thermal conductivity, creating temperature gradients across the stack. Often the most power-hungry die, like a high-performance logic die, is placed in the middle for routing and signal reasons. That means the hottest component is also the most thermally isolated, surrounded by other dies that act like blankets. Internal hotspots can form long before the outside of the package looks hot. Engineers respond by reordering die placement so high power dies are closer to cooling surfaces when possible, splitting a large die into several smaller ones to create spread power, using power aware techniques like clock gating so not all high power blocks peak at once. Combining with better materials and vertical heat paths, these strategies help keep up temperatures within safe limits and protect device reliability. In 3D ICs, TSVs, microbumps, and redistribution layers (RDLs) for short, are more than electrical features. They are also thermal paths. Metals such as copper and tungsten conduct heat far better than silicon or polymers, so interconnects can act like thermal conduits. If they're poorly placed, however, they can leave thermal dead zones where heat has few escape routes. To avoid this, designers use multi-physics simulations that couples electrical and thermal analysis. They tune TSV density, size, and placement to satisfy both timing and heat spreading. Interfaces between dies, underfill materials, and encapsulates are equally important. Voids or poor contact create high thermal resistance. Even when bulking materials are good conductors, careful selection and characterization of bonding materials and ensuring stability under temperature cycling can reduce overall stack temperature by several degrees, which has big impact on lifetime and reliability. Thermal vias and TSVs act like tiny metal chimneys, giving heat low resistance pathways from interior regions to surfaces where heat spreaders and sinks can work. Their effectiveness depends on geometry, diameter, length, aspect ratio, as well as spacing and fill material. Too few thermal vias leave hot regions isolated. Too many consume area, complicate routing, and may affect mechanical integrity. In practice, designers combine signal TSVs with dedicated thermal vias, concentrating extra thermal paths near high power regions. Modern fabrication enables vias filled with high conductivity materials such as copper, coppered diamond composites, or carbon based structures. These allow thinner stacks and higher power operation while respecting temperature limits. As power densities rise, co-optimizing TSVs for both electrical and thermal roles will remain central to advanced packaging design. Once heat reaches the package exterior, it must be spread and dissipated effectively. Heat spreaders, often copper, aluminum, or composites, sit on top of the package and distribute heat over a larger area so that heat sinks and fans can work effectively. In multi-die SIPs, spreaders help reduce temperature differences between high power and low power chips. High-performance SIPs, such as those for networking or AI, often include embedded cooling inside the package. Examples include microchannels etched into the substrates with liquid coolant, vapor chambers that move heat via phase change, localized cooling structures placed under the hottest components. Some designs also use phase change materials, PCMs, to absorb energy during short bursts and then release it slowly, flattening temperature spikes. By combining spreaders with embedded cooling, engineers build a layered thermal defense from the die level up to the system level. Thermal interface materials (TIMs) may look like simple paste or pads, but they are crucial. Even smooth-looking metal surfaces have microscopic roughness that traps air, which is a poor thermal conductor. TIMs fill those gaps with a thermally conductive medium, greatly reducing contact resistance. Engineers choose TIMs based on thermal conductivity, but also a viscosity, mechanical compliance, pump-out resistance, curing behavior, and long-term stability. In multi-chip modules, thermal pads are popular because they're easy to handle, can be cut to shape, and cushion fragile dies and solder joints. Thermal greases and gels can offer higher performance, but are harder to apply consistently in volume production. Recent research explores TIMs enhanced with silver, graphene, or carbon fibers to boost conductivity without losing mechanical integrity. These advanced TIMs can be expensive, so designers must weigh cost versus thermal benefit. The right TIM choice can mean the difference between a stable device and one that constantly skirts thermal throttling. Hotspots are small regions that run significantly hotter than their surroundings. Even when the average temperature is acceptable, hotspots can speed up aging, alter timing, and limit maximum clock frequency. Mitigation starts with physical design, using thermal vias and optimized die placement, adding local heat spreaders or high conductivity pads near hot blocks, and avoiding clustering too much power in a small area. On the architecture and software side, on-site thermal sensors track critical points in real time. When a hotspot forms, the system can respond with dynamic frequency scaling, voltage adjustment, power gating, or workload migration. In multi-core processors, tasks can be moved away from a heating core. This combination of static layout choices and dynamic runtime control lets chips push performance close to physical limits without crossing unsafe temperature thresholds. Dynamic Power and Thermal Management (DPTM) coordinates sensors and control mechanisms to keep devices within safe operating ranges. Sensors monitor temperature, voltage, and current, feeding that data into control algorithms. In laptops, DPTM shows up as the CPU or GPU, throttling briefly when a heavy workload raises temperature. In servers, it might distribute workloads across sockets or racks to spread thermal stress. In embedded systems, it can control fans, pumps, or valves, activating them only when needed to save energy. More advanced systems are beginning to use machine learning within DPTM. By learning workload patterns, they can predict temperature spikes and react early, reducing frequency or shifting tasks before a limit is reached. This predictive control minimizes oscillations and helps maintain smooth, efficient operation, making DPTM a key element of both performance and reliability. Before hardware is built, teams rely heavily on thermal simulation and modeling. Using CAE tools, they build detailed 3D models that include stacked dies, TSVs, interposers, packaging materials, and heat spreaders. Each component is assigned properties like thermal conductivity and specific heat, and boundary conditions such as ambient temperature and airflow. Simulations show how heat flow through the structure over time. Designers can quickly explore what-if scenarios. What if a hot die moves from the center to the top? Or what if we switch to a higher conductivity molding compound? Some tools also integrate electrical and mechanical models. Electrical models estimate local power dissipation, while mechanical models predict thermal expansion and stress. This helps identify not just hotspots but also regions vulnerable to cracks, delamination, or warpage under cycling. By iterating in software, engineers converge on thermally robust designs before committing to expensive fabrication. Simulations must be verified with real world testing, especially for stacked packages where many critical regions are hidden. Engineers combine several methods. On the surface, infrared IR thermography maps temperatures, revealing unexpected hot areas and confirming that spreaders and external coolers work as intended. To see inside, designers rely on embedded temperature sensors between or on dies, comparing these readings with simulated internal temperatures. Another key method is thermal cycling, repeatedly exposing packages to high and low temperatures. This stresses interfaces, solder joints, and materials in a way similar to long term operation. Changes in electrical performance or mechanical behavior can signal microcracks or delamination. By correlating simulation results, IR maps, and sensor data, engineers refine their models and confirm that the final package remains stable under realistic conditions. For our case studies, we'll briefly look at two real products where thermal management is critical: AI accelerators and RF front-end modules. First, in 3D IC AI processor modules, a high-power logic die is often stacked with high bandwidth memory, creating a very power-dense package. Designers use vapor chambers, micro heat pipes, dense thermal vias, and high performance TIMs, along with dynamic power management to pull heat away from the core and prevent power throttling. Second, an RF system in package modules for smartphones and base stations. Power amplifiers generate intense local heat. Materials like graphite sheets, thermal pads, and small vapor chambers, plus dynamic power control, keep temperature stable so RF performance and signal quality remain reliable in very compact hardware. Looking ahead, progress in thermal management will depend heavily on new materials and integration techniques. Researchers are exploring graphene, diamond composites, and carbon nanotubes, whose thermal conductivities far exceed traditional metals. Incorporating these into TIM spreaders or VFLs can significantly improve heat removal. At the same time, packaging architectures are evolving. Concepts like microfluidic cooling channels, self-regulating liquid loops, and hybrid air-liquid systems are moving towards practical use. We may soon see packages where coolant flows directly under the hottest blocks or where phase change materials are integrated at multiple levels to smooth out temperature spikes. As the industry moves towards chiplets and denser 3D stacks, thermal design will be central to system architecture and not just an afterthought. In summary, effective thermal management ensures that advanced semiconductor devices can deliver high performance safely and reliably. It requires collaboration between materials scientists, packaging engineers, circuit designers, and system architects. By designing heat paths as carefully as signal paths, we can continue to build faster, smaller, and more energy efficient electronics without letting temperature become the ultimate bottleneck. Thank you for your time and attention. We appreciate your interest in our work on thermal management in advanced semiconductor packaging.